The second speaker is Liang Jiang from Yale University.
Hi, thank you. So good morning, everyone. So first, I would like to thank the organizer, especially John, for giving me this opportunity to talk about our recent progress about the superconducting circuit and how to control these superconducting systems. And so first of all, this is a highly collaborative work with a lot of people from Yale. And you see like theorists, experimentalists, and several PIs involved in this work. And so let me first start with a brief overview of what's the current status of the superconducting circuit. And so here we're mostly focusing on superconducting cavities because they actually can have a much longer coherence time than the transmon qubits. So it has the potential that can be a much better quantum memory than just using the two-level systems of the transmon qubits. And this is basically the experimental setup. It basically consists of a chunk of aluminum with drilling of two holes, which correspond to two cavities, one for storage, one for readout. And between the two cavities, there's a transmon qubit, which bridge these two so that you can not only couple the transmon to a storage cavity, you can also use the transmon as a media to read out the storage cavity via the readout cavity. So and this simplified scheme is that a simplified figure is that you can think this as a storage cavity coupled to transmon. And that's what I'm mostly going to focus in today's talk. And of course, you also have the readout cavity, which actually can be efficiently used to read out the transmon qubits with a high fidelity and a QND readout. So one key figure of merit for this system, one key nice feature about the system is it's essentially described by this simple Hamiltonian, which consists of an oscillator, two-level system, and a strong dispersive cross-curl coupling. Okay, so first, this cross-curl coupling can be very large. It can be few megahertz, which is hundreds or thousands of times larger than the cavity loss, photon loss rate or the qubit decoherence time. So that opens the possibility that you can do a lot of controls over the system without losing decoherence. And in addition, as I mentioned earlier, with the readout, you can actually perform QND readout of the qubit with extremely high fidelity and in a very fast time. And in yesterday's talk, Irfan focused on about how to do these weak readout. And this time, in today's talk, I'm going to mostly focusing on strong readout of these qubits, if I needed any readout. So let's look a little bit more on this strong dispersive coupling between the two-level system and a harmonic oscillator, and what kind of controls we can have. So generally we have two types of controls. One is to drive the cavity or drive the oscillator by performing a microwave tone which is resonant with the cavity. And this drive you can perform in two regions. One is a strong drive, the other is a weak drive. A strong drive refers to the Rabi frequency, or the drive is much larger than the dispersive chi. So in this case, you can displace your cavity regardless of the state of the qubit. And on the other hand, you can perform a weak drive, which is have this epsilon to be much smaller than chi. Then you distinguish whether the qubit is in G or E, you perform different displacements. So this can be regarded as you can create a superposition of the cavity state depending on the state of the qubit. All right, and diagrammatically, you can show just this is a unitary gate on the cavity only, and this is a control gate controlled by the qubit. Or the second type of control you can have is to manipulate the qubit. And first of all, if you look at this Hamiltonian, dispersive Hamiltonian, you can see that actually the cross-curl can be regarded as a frequency shift of the qubit depending on the number of photons in the cavity. And if you look at the spectrum, the reflection of the from the cavity system, you'll find that actually it will have different peaks associated with the resonance of the qubits. And each peak corresponds to a cavity photon number state. So if you apply a strong drive with Rabi frequency much larger than chi, or n times chi, you'll find that actually you can perform qubit rotations regardless of the photon number in the cavity. Or alternatively, you can apply a weak drive with Rabi much smaller than chi. You can selectively displace your qubit, rotate your qubit for a specific photon number of the cavity. So with this, essentially it asks the question, are there m photons in the cavity? If there are, the qubit gets flipped. If there are not, the qubit does not flip. So combining these two types of controls, you can actually perform a quantum state mapping between the cavity and the qubit. And this is essentially we call it a QC map, a qubit cavity mapping process. So that initially the cavity is in a vacuum, qubit in a superposition state. After this unitary operation, the qubit becomes a superposition of coherent states, and the cavity, the qubit gets back to the ground state. And this is proposed in theory, and actually recently experimentally has been demonstrated. And if you want to see more, you can discuss with Brian, who's giving a poster today. And you can prepare the superposition of cat state of coherent states, and use the measure the Wigner function and see indeed there are Wigner fringes, so indicating that indeed it's a very good coherent superposition of these two states. And so far it seems that okay, we can do a lot of things with these coherent states, and the question is, can we prepare some other states, some like arbitrary superposition of photon number states inside the cavity? And in addition, besides preparing states, can we really actually perform quantum information processing tasks over these stored quantum memories? Or even if you ask more, can we perform some quantum error correction if we store the information inside the cavity? So that will be mostly the two questions I'm going to discuss in today's talk. The first is about the control of the cavity states. Can we prepare arbitrary superposition or perform generally like the unitary over the selected subspace of the photon numbers? And also consider quantum error correction. If I have time, I will discuss briefly about some tools we developed about the symmetries and the conserved quantities in these open quantum systems. So first, let's talk about how to control the cavity and the transmon. So first, as we discussed earlier, we can have a cross-scale coupling between the cavity and the two-level system. And we also have two kinds of controls. One is the cavity drive. The other is the qubit drive. So let's first go to the rotating frame of the cavity by removing the time dependence and this intrinsic energy of the cavity system. And then we can be more specific about our goals. So what we want to achieve is one specific goal is to prepare arbitrary states of the cavity system conditioned on the qubit is starting the ground state. And also the final state will also have a qubit in the ground state. Or if we want to be a little bit more ambitious, we can say, okay, can we achieve a unitary operation has such a property that when the qubit is in the ground state, the targeted unitary for the cavity will be a specified unitary, okay, with the fixed controls over a finite dimensional Hilbert space. And the strategy we're going to take is the following. We're going to alternate the qubit drive and the cavity drive. We never do them simultaneously because that makes life complicated. While when we drive the qubit, we always make sure we start in the ground state and end in the ground state of the qubit. And when we drive the cavity, we always consider the case that the qubit is in the ground state. Okay? So every time after each cycle of these drives, the qubit will always end up in the ground state. But what's non-trivial is actually the cavity gets a non-trivial evolution. So here is basically what the ideas are. So first, let's draw these level diagrams associated with this dispersive coupling of the qubit and cavity. So the horizontal labels are the cavity photon number, 0, 1, 2, 3, and the vertical levels correspond to the qubit in the ground or excited state. So first, allow me to assume that all these the qubit states are in the ground state, and the cavity can be in some superposition of the photon number states. And in this case, I first consider the qubit drive. And for simplicity, I consider one frequency tone, which is resonant with, say, m equal to 2. And with this drive, what I can do, fulfill the previous requirements, start in the ground state, end up in the ground state. The non-trivial thing I can do is to accumulate a geometric phase gate, which is, actually, one of Rob's postdoc, Rainier, come up with this good idea, is to do the following. You do 2 pi pulses. With one pi pulse rotate around the x-axis, and the other pi pulse rotated around some like a rotated axis. And you enclose a non-trivial area, and that area is associated with the geometric phase you accumulated. And because we're doing a selective drive, so basically this achieves a non-trivial phase only for the specific component n equal to 2. And for the other components, there is very little phase accumulation, except for some AC stack shift. And actually, the nice thing is that if we simultaneously drive these pulses, then the AC stack shift will be cancelled. So the dominant part is really this non-trivial geometric phase. And more specifically, we can apply these kind of frequency tones to drive these two pi pulses. And furthermore, we can actually apply simultaneous geometric phase gates for these associated with different photon numbers. It's because actually these omegas are very weakly derived. They never mix up with the photon number is always conserved, and also you can think these as effectively separate two-level systems that you're driving. And the nice thing is that you never need to worry about the rotating frames because everything starts in the ground state and end up in the ground state. There is no confusion about the rotating frame. So basically, if you drive these simultaneously with different frequency tones, then you can accumulate different phases associated with a different photon number. And what this does is achieving a simultaneous geometric phase gate with this phase. For a different photon number, you accumulate a different phase. And we give this a name called a selective number-dependent arbitrary phase gate, a snap gate. Okay, so this is something which is a highly nonlinear gate, because if the phi n is proportional to n, it corresponds to a detuning. If phi n is proportional to n squared, it corresponds to curl. But we can design arbitrary phi n, so we can have arbitrary high orders of curl obtained from this snap gate. And so far we talked a lot about the qubit drive. We can also think about the cavity drive. But because we constrain ourselves to the ground state of the qubit, actually the cavity drive is quite simple. It's just a displacement operation, which described by this displacement operator. So now we have two tools correspond to the snap gate associated with the qubit drive and the displacement gate associated with the cavity drive. So now I want to show that actually with these two controls, you have a universal control over this harmonic oscillators. So to show this, I'll give you two kinds of proofs. One is about this less constructive but more rigorous proof. Say we have a small time evolution tau, and suppose the phi here is a vector associated with a different phase accumulation associated with different photon numbers. Suppose the first m entries of the phi, which correspond to photon number 0 up to m minus 1, has a small phase accumulation tau. And this is the vector phi. And the displacement alpha is also something small proportional to tau. And we can perform the operation snap gate with minus phi, displacement minus alpha, snap gate with plus phi, and displacement with plus alpha. And this operation, if you do the computation, you'll find it corresponds to a two-level exchange operation between m and m minus 1, which is the leading order. And all the other terms are in the higher order. So this effectively gives you a control over two-level system between m minus 1 and n. So this actually breaks kind of all the trouble with the harmonic oscillator, which are equally spaced. Now we can selectively address two of the levels associated with the harmonic oscillator. And furthermore, this is the previous approach with small tau is less constructive because it requires infinitesimal evolutions, which is difficult to achieve. Now we can actually consider finite step evolution associated with phi and alpha. Let's say phi is associated with either 0 or pi, and for simplicity, we assume that the first m entries are pi, and the rest are 0, which you can achieve by geometric phase for the first m entries and associated with the photon numbers, and don't do anything for the rest. And for displacement alpha, it will be a function of some parameters of m and the rotation angle you want to achieve between these two levels. And it turns out that we found using 5 pulses, you can do a very good job achieving a unitary rotation between m and m minus 1, these two levels. And the fidelity can be higher than 99%. So basically, you're alternating your qubit drive and cavity drive. You can achieve a selective two-level coupling between m and m minus 1. So here's just some table, give you the value for increasing m. You find that alpha actually decreases. And phi has the pattern as we designed, and the fidelity actually can be always higher than 99.8%. And here I'm just saying 5 pulses. If you do 7 pulses, the fidelity can have 4 nines. So it's just a very efficient and robust scheme to achieve a selective control over two levels. And here is associated with different angles you want to rotate. You'll find that, okay, these numbers actually can be very good. So basically, you have a very robust control at the unitary level for selected numbers of photons in the cavity system. So let's look at some applications about these snap gates. The first one is one can deterministically create the photon number states. Suppose we start from vacuum, and we apply some unitary operations correspond to two-level rotation between 0 and 1. We can deterministically prepare a single photon state inside the cavity. And notice that this is a deterministic procedure because, as compared to the earlier cases that you can do photon number measurements, heralded on the measurement, based on the measurement results, you can prepare a single photon. And this is single photon on demand. And so here is the procedure. So instead of 5 pulses, actually for this single photon case, it's easier. You can do 3 pulses. You first displace the vacuum with alpha equal to 1.143, which is optimized for this calculation. And then after this displacement, you'll find that actually the photon has some distribution, which is associated with the mean photon number to be this alpha square. So these are the photon number peaks with 0, 1, 2, 3, 4, and so on. Then you apply a snap gate associated with performing pi pulse for single peak associated with photon number equal to 0. And what you find immediately, actually, this thing, there's a hole in the middle, gets negative Wigner function. And the distribution doesn't change too much because the snap gate doesn't change the photon number. It only shifts the relative phase. Then you displace this state back to the origin with minus alpha. And what you find is you actually get a very nice single peak associated with a single photon inside the cavity. So what I should mention is this is a preliminary experimental data. It's not a simulation. So it seems that we have good control over the system. But in order to go more, we actually need a very good coherence for the cavity and the qubit if you want to do lots of these gates. So I think we're pushing along this direction, and in principle, one can produce arbitrary superposition of photon number states. And there's one thing I should distinguish from the previous work is that earlier, like theoretically, Eberle and Lowe proposed similar proposals to create arbitrary superposition of photon number states. But that was based on a Jens-Collins model. And here, what we are assuming is actually a strong dispersive model. So it's a different Hamiltonian. And also for JC model, it's a little difficult to construct a unitary evolution because what they propose is to construct a quantum state. And also, similar demonstrations also have been experimentally demonstrated in trapped ions or superconducting circuits, but those are all mostly all based on JC model. And this is actually based on the strong dispersive model, which the nice thing is that actually this one, the cavity and the qubit are well separated because they don't exchange excitations. So you really have a good control over the cavity, which can stay in the cavity without additional tricky issues with the coupling to the qubit. So the second application, also for the snap-like gate, is the following. You can efficiently read out the photon numbers inside the cavity. So as we know that earlier work that by Sergei Horosh, they can read out efficiently photon numbers inside the cavity using QND schemes and the maximum likelihood estimate or different other approaches. And here we can actually also do similar tasks, but probably in a more efficient way. First, you can think the photon number as represented by a binary, just like what computer does. And what we want to achieve is read out these binaries one by one. And if we can do this, we can read out like a photon number with millions of photons with probably just 20 readouts. And so here is the idea. So first, what you do is to excite the qubits if the number of photons is even. And then you read out the qubits. If it's excited, indicating the binary B0 is 0. If it's not excited, indicating the B0 is equal to 1. And then you get the first binary. The second binary, what you do is you excite the qubits if the photon number is 0, 2, or 4, or 5, which is equal to 0, photon number equal to 0 or 1 modulo 4. Then you measure deterministically B1. And similarly, you can measure these photon numbers modulo 2 to the k with these results. And basically, you can extract these binaries independently, one by one. And because we have a high fidelity readout of the qubit, we can read out these binaries with high fidelity. And the scaling is the following. So basically, you only need log 2n number of measurements to measure all these binaries, where n is essentially the upper bound of the photon number you want to measure. And notice, we don't need any feed-forward control because these measurements essentially is independent. But this is kind of in comparison with what the earlier schemes which people did with the Ramsey-based schemes. And the scaling, basically one needs roughly order n measurements to find out the photon number. So if the photon number is large, this is actually exponential improvement in terms of reading out photon numbers. But of course, I should also mention that recently Hiroshi's group also did an experiment with the feed-forward control so that they can actually, in principle, push this number to the similar scaling. But the difference is that here we're not doing the Ramsey. We actually have a selective photon number based gate, like a snap type gate. So that actually makes it more powerful and more efficient to retrieve these informations. So far I talked about, okay, this is just a comparison. We can basically, if you want to distinguish 8 photon number states, you do 3 measurements compared to about 20 measurements earlier. And if you want to have 125 photon numbers, you do like 7 measurements, and previously we'll need like probably a few hundred measurements. So it is an exponential improvement. And so now let's talk about the second topic, which is about the quantum error correction. And the questions we are going to address is the following. Can we store quantum information longer than the lifetime of the cavity? Oh, here it should be the coherence lifetime of the cavity. Because if there's a photon loss, can we still maintain the quantum information and correct the errors? And in addition, can we also perform quantum logical operations over the encoded states? And we think that the answer is yes. And this is, so let's maybe be more specific about what we want to fight against. First, we want to fight against the dephasing error, which is characterized by this quantum, Lewisian with the dephasing kind of associated with the photon number operators. And also there's the photon loss operators, that photon loss errors which we also want to overcome. And notice that the dephasing error doesn't change the photon number. So basically, you can think that the environment is essentially probing the photon number. And one way to overcome this dephasing error is actually if we can shuffle the photon number really fast. And from the environment perspective, it sees on average the photon number looks the same for different quantum states. Then the environment will not be able to extract any of the encoded quantum information. And for the photon loss error, the strategy is actually to monitor the photon number parity. And this is actually earlier proposed by Mazia and Zaki early on. And it turns out that we can actually combine these two things together. So here is the idea. Let's start from something very simple, which is a driven damped harmonic oscillator. This is a drive, this is a damping. And first of all, we can write this in a simpler form as with a coupling operator being A minus alpha to infinity. And in this simpler form, life is simple. And it's easier to see why there is a steady state, which is the coherent state of this driven damped harmonic oscillator. Because it's annihilated, it is eigenvalue 0 for this coupling operator, which means the coherent state acted by this operation, it's 0, which means the coherent state is a steady state with no dynamics. And for this case, one can show that there is only one steady state, so the system will be automatically driven to this specific state, regardless of what the initial states are. So, and you can find the relation for this alpha infinity as a function of the drive and the damping. The stronger the drive, the larger the alpha, the larger the damping, the smaller the alpha. And well, this is actually a very nice physics, but for our quantum information purposes, it's not enough because we only have one steady state, which will not enable you to store any of the information. So what we want to do is the following. Replace A by A to the power D. And similarly, this magic still holds. You can still do the coupling operator with A to the power D minus alpha to the power D. And for this state, you will find that actually there are D coherent states, which has eigenvalue 0 for this coupling operator. And the coherent state amplitude is alpha, and it corresponds to, for D equal to 2, it's plus alpha and minus alpha. And for D equal to 4, you have 4 such coherent states, which vanish, which are kind of annihilated by these operators. And what's more important is the superposition of these coherent states are also steady states of this evolution. So essentially, you get a d-dimensional Hilbert space, which are steady states of this operator. So you get a very nice encoded states, and this is actually closely related to earlier works about the decoherence-free subspace and lots of these related works. Yeah, but here we're mostly studying the dynamics about how to approach this decoherence-free subspace. And so actually, if you want to know more details about how to create A to the D and how to achieve these operations for D equal to 2 or D equal to 4, I would highly recommend to watch Mazia's video talk, which is recorded on August 1st. And also, I would also recommend that take a look at this paper, because we actually have lots of details in there, which I think it's the first time that these things are proposed. So in addition to that, here is just to get some idea. Suppose D equal to 2, we can have some initial states, depend on different initial states. You'll find it go to different steady states. And actually, this proposal for D equal to 2 has been carried out experimentally by Zaki. And he's also here at the conference, and I would recommend to go to his poster and chat with him, because here what I'm showing is the Q function, so you don't see fringes. And in Zaki's poster, there will be fringes because he's measuring Wigner functions. Okay, the fringes are important to verify that it's a coherent process. Yeah. So finally, now let's talk about the coding, because so far I kind of talked about from this the driven perspective, it's natural to consider superposition of coherent states with equal amplitude but different phases. And actually, there's another reason to consider this coding. It's because those codings are actually mostly insensitive to dephasing. So the idea is the following. Let's consider encoding the 1 bit of information using 0 and 1 photon in the cavity. And this is a Bloch sphere associated with the state. And you may notice that the average photon number is 0 for the 0 state and 1 for 1 state. But this is actually causing the vulnerability of dephasing errors, because the environment essentially is kind of measuring how many photons are there, and they will see the difference whether it's 0 or 1. And that causes dephasing. And even worse is that if there's photon loss, you cannot restore the information, because everything goes to 0. You don't know where the initial state is. So now to overcome this first dephasing error, let's consider the following. Let's apply the 2-photon pump and 2-photon drive. And as we know earlier, it will drive to the steady state. If it's 0, it will drive to the even photon number steady state, which is a symmetric cat state, alpha plus minus alpha. And for 1, it will be odd state, which is alpha minus alpha. So that's what's going to happen. And for these x direction, it will be coherent state alpha and coherent state minus alpha. And the key feature, so we can redefine it, basically alpha plus minus alpha, we call the logical 0 state in the z basis, label it as C alpha plus. And alpha indicates amplitude, and plus indicates it's a symmetric combination. And C alpha minus indicates it's an antisymmetric combination of the coherent states. And the key feature is this state, it has even photon numbers, and the state in the lower has odd number of photons. And if you look at the distribution, it does have even and odd, which kind of put a filter of even photons over Poisson distribution. That's what you get. And the nice thing is, first you will see the Wigner functions with the fringes indicating even and odd and coherence. And similarly, you can also look at the plus alpha and the minus alpha states, which also has a Poisson distribution. The key feature is the states, these 4 states, and actually all the states on the Bloch sphere or inside the Bloch sphere has a key feature, is that the average photon number is essentially the same. The difference between them is exponentially small with respect to alpha. So if the environment only cares about the average photon number, then the environment cannot distinguish any of the states on the Bloch sphere, which gives a protection against the dephasing noise. Okay. So, but of course, we need to make sure that the environment only cares about the average photon number, not a specific photon number, which can be achieved by strongly drive the system, injecting and taking away photons with our engineered dissipation. And to prepare for next stage, we want to also correct the photon loss errors. So let's go a little bit further. Instead of coherent states alpha plus alpha and alpha minus alpha, let's consider coherent states alpha, minus alpha, I alpha, and minus I alpha. Then this superposition will have 4n photon numbers, which correspond to north pole. And the south pole correspond to which we have 4n plus 2 photon numbers. So you may notice that these 2 logical states has even number of photons, which defines the logical subspace. And if there's a photon loss, it will go to odd number of photons, which if we have a photon number parity detection, we'll be able to identify there is a photon loss error. So that's why actually and we want to go to a little bit more sophisticated with 4 coherent states. And similarly, you can define plus x and minus x. And, but the key feature is still the same. That's the average photon number on or inside the Bloch sphere is exponentially similar. They have differences exponentially small with alpha. So with these things, we can now look back about the defacing error. So you'll find that actually the defacing error has a feature that it doesn't change the photon number. And hence it will actually have some preserve the even and odd, or modulo 4, whether it's 2 or 0. So it doesn't cause any bit flip errors in the Bloch sphere we defined. So mostly it will cause just a defacing error or loss error, which is leakage to the non-logical states. Now let's put these together with this engineered dissipation and drive and dissipation, and combined with the defacing error. And one can perform a numerical calculation, and actually for some of the cases we can even do analytically with the tools we developed, and it's actually the following. So first of all, this system has 2 dimensionless parameters. The first dimensionless parameter, you can say alpha, which is the ratio between your multiphoton drive and multiphoton loss. That determines where the steady states are. And another dimensionless parameter is the defacing and the dissipation, multiphoton dissipation. That tells you essentially how fast the defacing compared to your shuffling around the photons. Okay, so what you want is alpha to be as large as possible, so that the photon number will become almost the same. And at the same time, you want the kappa phi to be much smaller than kappa d, so that defacing is small, so that you can shuffle the photon fast enough. The environment only cares effectively about the average photon number. So in this case, you'll find that here this is for 2-photon process with injecting takeaway 2 photons. You'll find that this curve essentially, so these are actually 3 curves, correspond to as a function of alpha, with the kappa phi over kappa d being 0, 1 over 200, 1 over 20. You'll find that it's essentially the same. What it means is that if you have alpha sufficiently large, you'll have very little defacing, even though as long as this number is less than 1, essentially. And so it's basically, and also what's important is the tail here. Actually, we should plot a log linear plot. Actually, this tail indicating that this defacing rate, effective defacing rate at the logical space, decreases exponentially with alpha. So the larger the alpha you have, the less likely you will have any defacing error. And that suppression is actually exponential. And actually for that intuition, there's also Mazio in his talk also discussed about some of the intuitions, which due to the time limit, I probably won't have time to discuss it. But it's really like a separation, and it's like a tunneling with some a dissipative gap or some a coherent gap. Yeah. And similarly for 4-photon process. Essentially what we get is exponential suppression with a cat size for the defacing error. And now let's look at the photon loss error. And as I mentioned earlier, the strategy is to monitor the parity. If we start from a subspace with even parity, if there's a photon loss, you go to odd parity. And when you measure the parity without extracting photon quantum information, you have a chance to restore the information. And so probably, I think I'm a little bit running out of time. So the key idea is the following. The 2-photon process with injecting or taking away 2 photons at a time, we can suppress defacing error very efficiently. But unfortunately, it doesn't correct bit flip errors because the logical states are even and odd states. That's why we need a 4-photon process to create 4 superposition of 4 coherent states. And the logical states is in the odd, even photon numbers. And if the photon loss, we can identify. And if the defacing error, we can also autonomously correct them. So therefore, I think regarding the task about how to correct defacing and photon loss errors with these coding schemes, then it actually can nicely resolve both of these issues. And so now there's another task. How can we do universal control over this encoded space? And this is actually a little non-trivial, but I think actually during the meeting, actually there are lots of discussions, and there's one nice talk by Daniel about this quantum xenodynamics, and this is exactly one nice example for that. So basically we have this engineered drive and dissipation. You can think together as some dissipation with some jump operator. And if we drive the system, now let's consider for simplicity with a 2-photon process with coherent states alpha and minus alpha. If you drive the system with a displacement along the p axis, you'll find that actually it will induce a logical operation within the subspace. The condition is first the following. Epsilon x should be much smaller than kappa 2 phi. And in this case, we will find let's consider discretized time. Suppose there's a small displacement followed by a strong dissipation. And small displacement will drive something, will drive the steady states, which are superposition of alpha and minus alpha out of the plane. And then we do a strong dissipation to map everything back to the steady state subspace. And there will be a non-trivial projection in the steady state subspace, which corresponds to the unitary evolution in the logical space. And that is actually correspond to, you can change the parity a little bit by doing this displacement. And it actually corresponds to the Wigner fringes is horizontal. When you do this vertical displacement, it changes the parity. Okay, but so in similar fashion, we can develop all kinds of unitary controls. Arbitrary rotation around x, pi over 2 rotation around z, but this time we need some curl effect, which is something not perfect because it may, during the curl effect, we may suffer from dephasing noise. But this is, but if the curl is stronger compared to dephasing, this will be the error can be well controlled. And also we can do two-qubit entanglement with such coupling Hamiltonian combined with the controlled dissipation and the drive. And for 4-photon process, essentially just square all the A's, you get a similar couplings. So this is kind of the part that we want to discuss about this universal control and the encoding. So in the last minute, let me just briefly mention a related work and some tools we developed while working on this project. It's related to the symmetry and conserved quantities in open quantum systems. So generally, there's when we learn physics, we know that for unitary evolutions, for closed quantum systems, if there is a symmetry, they will correspond to some conserved quantities. And for these open quantum systems, what are there such correspondence? And actually, we see something like this because for these jump operators, you'll find that the photon parity is preserved. And it turns out, yeah, the final state's parity also preserved. But there is even more than that, because not only the parity is preserved, population preserved, there are some coherence between even and odd is also preserved. And that pushes us to think, okay, can we find some conserved quantities associated with these coherences? So let's just look at one example. Suppose we have this 2-photon driven dissipation, and we can find the steady state, which will be in the two-dimensional Hilbert space spanned by our logical states. And the plus or minus correspond to even and odd, and here correspond to the coherence between even and odd. So notice that we have kind of 4 numbers here, and actually each of these numbers is a degree of freedom that's associated with the density matrix. Of course, you need to be Hermitian for these cases as well. Yeah, and each of these numbers associated with some degree. And it turns out that for each such degree of freedom of the steady state density matrix, there is a conserved quantity that we can find. And it's unique. And for this conserved quantity, we can compute such such coefficients associated with the steady state from the initial state. It's just a trace of this operation. And explicitly for this example, we can construct these operators. Here is just the population in the even states, which is expected. But this animal is something which we're not less familiar with. But it's actually something conserved, because if you consider in the Heisenberg picture, the evolution of this operator is 0. So it's a conserved quantity. And you can use this conserved quantity to compute these off-diagonal elements. And computational-wise, this will give a square root of improvement in our computation, because in principle, one way to do it is you do this thing, exponentiate over your Lindblad over infinite time, you get your steady state. But that involves exponentiation of n squared by n squared matrices. But if we know these conserved quantities, it will be n squared by n, or it will be n by n. And you can compute these conserved the final steady states more efficiently. But I think that it's actually helped a lot when we do these calculations about the steady states, because actually for these cases, we can get analytic solution for the whole system. But when it gets more complicated, so far we haven't get analytic solution for 4-photon pump cases. And maybe because of our lack of knowledge of these special functions. But we think it should be there. Yeah. But another key nice result is the following. The number of conserved quantities is equal to the number of degrees in the steady state density matrix. So this actually points a direction that if we want to study those open quantum systems with multiple or with high dimensional steady states, these conserved quantities might be something one should look into. And And it will provide a nice tool to efficiently compute the steady-state properties. And also during the evolution, we find that actually these conserved quantities doesn't change even though the states may evolve crazily. So that's actually another thing indicating, okay, maybe if we want to if we really care about the quantum information stored in the system, maybe we should look at these conserved quantities. And another thing is actually we used in this paper is actually these conserved quantities allows us to do some perturbative calculation of if there's other decoherences. And actually for some earlier plots, if you remember this function of alpha, there's a decoherence. Those are actually the perturbative calculation based on these conserved quantities. And that gives some analytic curve which fits nicely with the numerical calculation. So with this, and just to summarize, so first I talk about arbitrary control, and the take-home message is that we can do some snap gate for this photon number-dependent arbitrary phase gate. And that's something which probably people are less familiar with, but actually it's there for the superconducting circuit systems. And also for the quantum error correction, actually with engineered driven and dissipation, you can actually create a non-trivial steady-state subspace, which allows you to store information. And if there's any dephasing, you can autonomously correct those dephasing errors. And combined with the parity measurement, you can correct both dephasing and the photon loss errors. And combine some additional drive, you can achieve universal control over the system. And finally, there is something about the symmetry or conserved quantities, which personally I find is actually interesting because you may look at, even use these as tools to study these open quantum systems with non-trivial steady-state subspace. Yeah. So given that, I think that's all I want to talk about.
On your last point on symmetries,
yeah.
It would be very easy to see that result if instead of writing your steady-state density operator in terms of coherent states, you write it as a normally ordered power series at A and A dagger, and then you just, the various terms are just your conserved quantities. And all that generally.
Yes, I agree. And actually, our work, I should mention, our work is also partly motivated by your work on this cooling the cat. Yeah. but unfortunately, hopefully that come out soon with somewhere.
Yes,
yeah.
With a different title.
Oh, I see.
Editors didn't approve of Cool for Cats as an appropriately somber title.
Yes.
Yeah, I also had a question for my own clarity, at least in regard to these symmetry conserved quantities, because coming from quantum error correction and noiseless subsystems is a fairly, to me, old idea.
Yes.
If I am understanding correctly, what you have is like the condition for having a noiseless subsystem in the system. But what I wanted to understand better is if there is also an attractivity feature to it, or namely that the dynamics attracts to that noiseless subsystem. Or in the first part, for sure, if I understood correctly, when you have the A to the D, the annihilation operator to the d power, you have the subspace which is steady and attractive. Is that correct?
Yes.
So in your last part, is it just in quotes a noiseless subsystem in a Markovian Lindblad regime, or is it also additional features to it?
Yeah. So far, what we have is that these proofs works for the master equation Lindblad systems. And actually, we had a nice referee comment about if can we consider stochastic systems in there, but we don't have a complete answer to that, including the noise. That's but also for this case, there's another little complication is that if you may have some non-trivial Hamiltonian evolution in your
what I mean by noise here is just the generators of the dynamics under which this is unaffected. So.
Yeah.
Not that I mean extra noise on top.
Oh, if you have noise and which kind of commutes with these things, yes, it will perform a logical operation over the system.
Right.
Yes. Yeah, but I agree that this is closely related to decoherence-free subspace, and my understanding is the connection is really this is more closely related to the physical system
in general, because as you said, the state can evolve like crazy.
Subsystem. Yeah.
And that's what I was trying to understand. So the idea of the subsystem.
Yes.
Nice talk. The question about how one can improve the error correction
you talked a little bit about making the cat bigger, and that can make it better. But because my intuition about QEC is so dominated by stabilizer codes, I also want to think about how you might be able to concatenate the code. Would you do that by adding more legs to your cats? Would you add another optical cavity in there? All of the above?
Yes. So first of all, it is related to quantum error correction, and we're working on this. And the connection is, first of all, you can think this is the four-dimensional Hilbert space to encode one bit of information. You get one bit of redundancy to detect the photon loss error. And putting a more like error correction language, you may care about the distance of your code. And here it's an asymmetric code with respect to dephasing and photon loss. Photon loss distance is 2 because you only detect the loss, you cannot detect gain for this coding. But you can put more coherent states to increase the distance of photon loss. But for dephasing, the distance is actually alpha square because it takes that many steps to go to here. But another, for more technical audience, this is most precisely described by approximated quantum error correcting codes. And because these coherent states are not exactly orthogonal. So that actually leads to some complication if you want to really analyze this error correction. But this is something we're actually thinking about this. And so in principle, we can increase the distance of the code by going to larger alpha and more legs for the cats. But on the other hand, larger the alpha, the more likely you have photon loss. So there is a compromise between the two. Yeah.
If you are saying that there are two error models which here overlap, the dephasing one and the photon loss one,
yes.
Where for the first one you can nicely error correct, while for the second it gets more intricate. I think this is an invitation for using numerical optimal control and really try to minimize the photon loss type of errors by your pulse schemes, because then you combine, so to say, error avoidance by optimal control with error correction on the part which you can handle very properly. And I think this would be a very nice match of two different strands of techniques.
Yeah, I agree that here that I'm just assuming that you do like a strong projective measurement of parity. Maybe one could consider some like weak measurement of parity, but the issue is that it takes a similar amount of time because we're kind of doing the qubit to probe the system. It's but yeah, and also that the measurement may have errors or may introduce more errors, and there's also an important question about fault tolerance of these systems. So yeah, I think there are still lots of things we can study and probably combined with what you propose. Yeah, it would be good to discuss.
One last question.
So do you really need to generate these four component cats by this dissipative multi-photon? I mean, you could generate in other ways as well, right? And that still work?
Yes, there are actually other ways to generate it, and actually it's work by Zaki and Mazia early on. Is that principle with the QC map, qubit cavity mapping, you can kind of perform qubit-dependent displacement.
Yeah.
That allows you to generate similar like encoded states. But the nice thing about this is that if we start from vacuum, we apply your pump, ideally it will go to one of the logical states, and that gives a natural initialization of your codes.
So the pump also gives the dissipation, the many photon dissipation?
Yeah, actually in the implementation-wise, yes, it actually does both at the same time. So the idea is that you introduce another very lossy mode, which associates with the multi-photons. And if there's this lossy photon is lost, correspond to taking away multiple of these photons. Yeah.
Okay, so let's thank the speaker again.